Dr. Jothiramalingam, Aditya Engineering College, Vizag, who is a great profound researcher in his field. Now I request Ms. Brinda Ramasubramaniam to address the speaker, and I also request all the participants to switch off your mics and videos. Thank you.
Yeah, once again, thank you, Varshini. Good evening to all the participants present here, all the faculties, professionals, and students present here. On this auspicious day, with much delight, I welcome our speaker, Dr. Jothiramalingam, Aditya Engineering College, Vizag, Andhra Pradesh. Dr. Jothiramalingam completed his in nanoscience and technology. Dr. Jothiramalingam has completed his master's degree in nanoscience and technology and PhD in School of Material Science, Energy and Environment Division from Japan, in Japan Advanced Institute of Science and Technology. He also completed his postdoctoral degree in School of Material Science, Energy and Environment Division from Japan Advanced Institute of Science and Technology. His specializations are graphene-based advanced nano electromechanical switches and sensors. And now he is working as a design consultant for various nano electronic design firms, including Siemens. He's one of the great researcher and a good academician. So with much delight and honor, I welcome Dr. Jothiramalingam for his valuable lecture today. We welcome you, sir. Please take your turn, sir. Sir, please unmute your mic, sir. So that your audio will be... Yes.
Can you hear?
Yes, sir. Yes. Yes, sir. Very able to hear.
Yeah. Hi to everyone. I'm Jyoti. We are going to discuss some small aspect of nanoelectronics today. Before starting the session, I would like to thank the organizers for conducting this online web-based seminar. Thank you all. Let's discuss some subject. I'd like to share my screen.
Yes, sir, please.
Can you able to see my slides?
Yes, sir, we're able to see.
Okay, let's dive in. Today we are going to discuss perspectives of 2D materials as an alternative for CMOS electronics. It looks like very complicated title, but it's actually not. It's very simple. I assume the audience are very diverse range from students to very seniors to me. So I would like to construct this webinar in a way that anybody can able to understand. We'll go by very slowly, and then we pick up some very interesting research results that we are listening. In correlation with the 2D materials. Okay. Now we are driving in a kind of conclusion that the 2D materials can be alternative for CMOS electronics. So that's an outline. Actually, this is the outline that I prepared at the end of my PhD. Okay, you just look at the outline. It starts with the limitations of CMOS technology, and all the way we are using this alternative 2D materials as an alternative for CMOS, and then we try to conclude this can be potential candidate for future electronics. That's what I did in my whole PhD. So today we are going to see the same thing, but before that I would like to tell you two different story. Maybe this story is for the younger audience. They can able to get into the subject very easily. Okay, that's the background story number one. As you can see, there's a family, and this family is in early 2000. Okay, let's say the father of the head of the family decided to buy a cell phone. Okay, so what do you do with his cell phone? Okay, he can distant people call, Also, he can able to send a message to distant people by text message. That's the maximum. Primary. This is what we call as a primary applications of a cell phone at the early stage of 2000. Okay. So, what are the secondary things you can go? You can probably set up an alarm, put a reminder note. That is maximum application until the 2005. If you take in a cell phone. For example, let's consider a family in 2010, okay, maybe late 2010, which means after 2015. If they decided to buy a mobile phone, literally they can do everything, right? You can send a message, you can text them, not only in text form, you can text them in message, you can text them in the video, you can do, we are literally conducting this webinar with the help of cell phones, and most of them listening to me through the cell phone. The mobile devices are having a very drastic exponential growth in the last decade. That's a very dramatic thing. This dramatic improvement and development in the communication as well as the electronics leads the potential problem that really shakes the base foundations of CMOS. Okay. So far we are discussing family in two different timelines. Then they just got the mobile phone, and then what is the advantage and disadvantage? They are there. Okay? This is not very difficult. It's much easy to understand. You can see this is a very template diagram. As you can see, this is an evolution of the cell phone that we are using, and then there's the very old that we are aware of it, and then the current model that we are using now, smartphones. Okay? As you can see, the evolution of the cell phone or any mobile devices comes with the evolution. The evolution consists of three main characteristics. One is the miniaturization. Okay? From the time the CMOS, the BJT was invented, from the time the Moore started this Intel phone company, okay, their single most and profound idea is to shrink everything down. Okay, that's the single most motto they have for the last more than decade. So they reduce the size. Meanwhile, they also reduce the cost, and then they they certainly increase the efficiency. Efficiency in the sense that you can consider your father's first mobile to your first smartphone. That's the efficiency. It's too drastic thing, right? So this comes at a cost of a disadvantage. One very important. There are many disadvantages. One is power consumption. Okay? The mobile phones, your normal smartphones consist more power, and then it generates more heat. So excess power, it's very very easy consequence that it produces very excess heat dissipation. Okay, that's the take home message for the story one. Okay, you always start from, let's say, 2 decades ago. You drastically improve your system, by following all the electronics industries, prime goals, and then you end up with two important problems. One is high power consumption, and then excess heat dissipation. Just say you have two messages now. Now let's move to story number 2. Okay, this is another story. You consider a family, a very small family, 2 kids. Okay. As you can see from the figure, this one kid is kind of naughty guy, and then little bad guy. The another guy is a very kind of good guy, as you can see here. So one good guy, one bad guy. Okay? At the beginning, you have to take both of them, as your child, and then you can go along with their life. As times go by, one guy progress in a way that he want to progress. The other guy progress in other way that is not so quite good for the family in general sense. Okay, up to certain time, let's say you have a kid number 1, and then he's well and good in everything, he studied well, and then he move ahead with his career, and then starts to earn money, and so on and so forth. That's a very essential part to keep the system running. Okay, If the other guy pursues at the beginning stage, he didn't study well and then he spent all this time boozing and other things, that's not an issue until a certain point, okay? If the first guy says, okay, I'm so on so far good, so let's get married and then I would like to start a life, right? Maybe, let's say the father says, okay, you can get along with this. The second guy also says, okay, I'm also get along with my life, okay? This is kind of a situation, this is a kind of point in time, the system reaches its threshold, okay? You cannot, give a life to a guy who is not so good in his life and then boozing all the time, okay? This is kind of, it's a point where, family has to make a very drastic decision, okay? Exactly. If you consider our CMOS electronic as a family, now we are in a kind of situation, we have to take a very drastic measures to save the family, or otherwise it leads to a problem, okay? There you go. Now the good guy in the family is nothing but on-state power, means that on-state current actually, that produces on-state power. The bad kit is the off-state leakage power. Okay, we'll get to know further what is on-state and then what is off-state, so on and so forth. But before that, let's understand. There is one good guy that's essential for running the family. That at certain point in time he causing a problem. That's fine. The bad guy, in the earlier stage, he's causing a problem. That's no issues. But as time goes by, he causing more and more problems. That's not tolerable. That's the take-home message from the story number 2. Okay. Now let's say we also established the doctrine that the good guy is the on-state current, the bad kid is the off-state leakage current. Okay. I think most of you know about this, CMOS basics, but some of you might not familiar with the terms. So that's why I'm spending more time on establishing this. Right. Now this is the problem. Okay. Let's say on one hand you have a 20 years ago, like the mobile devices, you have a system. Let's say in early 2000, Core 2 Duo is the highest if performance processor that you can buy from the market. Okay, today you can buy Intel i7 10th generation processors. Okay, so the efficiency of the Intel i7th processor is much greater than Core 2 Duo, but it also comes with a cost like you cannot use your laptop for more than 10 minutes. It's burning from the inside. The heat dissipation is too much. Okay? You cannot able to stop. Okay, people from long time, at least more than a decade, they are telling they are solving the overheating problems. But this is a very funny image on the right side. It's like a cartoon image. The HP failed to produce any useful solutions for this problem. They rather produces it's a very sarcastic image. They produce hot fans to do that. Okay. Now another very important problem is when your mobile device or any electronics that consumes a lot of power, means it drain out your battery, right? This is another sarcastic image. It says connect to your high voltage battery to keep the system running for a long time. Okay. So this all comes from very, very tiny part. Okay, I myself, I'm not an application engineer. I'm also do not know much about how the multi-billion transistors are working or design aspects of it. I'm not much expert on that. But what I have worked in my research is I mostly spend on how to make a single device efficient one. Our problem is really limited to a single device. Okay, we take a single FET and then we'll try to produce an alternative for FET. That's the thing. Okay, so far we have established 2 doctrines. One is CMOS has a problem, heat dissipation, and then the heat dissipation comes from your bad guy, that's leakage current. Okay. On the other hand, you have mobile devices and all the communication devices as shrink in size. They are also having the same problem. Okay, because we come with the 2 different stories, but the problem of the two stories are, just single rooted. Okay, so that's what we are going to address. First we'll establish the problem. Okay, now let's back to my original outline. Now we'll discuss about my first outline. Okay, all right, here is your, if you take any mobile devices, any computing devices, you have a thing called processor. Okay, that processor is nothing but like billions of transistors stacked together in order to accomplish a common goal. That's the definition of it, right? The transistor, that is a very small, tiny, single unit of the processor. Okay, what we are mostly using is FET, field effect transistors. The field effect transistor is nothing but a switch. Okay, we do not want to complicate with too many technical terms. Let's say it's a simple switch. Okay? There is a graph that we cited from the reference. Okay, on the x-axis you have a length, gate length. On the y-axis you have a power dissipation. Okay, so the gate length is something you reduce. When you're reducing the, you can read the graph in the reverse order. From 10 micrometer to 10 nanometer. We're reducing the size of it. Why we are reducing the size? That is our prime goal in CMOS. Miniaturization. You consider your father's mobile and your mobile. We shrink the size. Okay, when you shrink the size, there are two things happens. Okay, the blue line represents dynamic power. Okay, that dynamic power is nothing but your good guy in the family. Okay, at 10 micrometer, he somewhere starts with 1 watt per centimeter square. That's his value. Okay, that's understandable, right? Fine. Okay, but the bad that standby power comes from the offset leakage. That somewhere starts from 10 to the power of -8 watts per centimeter square. Okay, so that's somewhere deep beneath the level. At the beginning he's not at all a problem to a family. Okay, when the times goes by, when the family is moving forward, when the CMOS industry is moving forward, the leakage current, you see the leakage current, it's drastically increasing. It reaches at a point where your leakage power makes a trouble with the dynamic power. Trouble is nothing but it reaches a point where the bad guy causes more problem and trouble than good guy in the family. To maintaining the bad guy itself a kind of a big problem. That's the problem. Okay, that's what I referred earlier as a threshold point. That's what we are now. Okay, that's the real problem we are facing. Okay, that's the root of the problem. That is what we are all going to discuss all this. Let's say 30 minutes. Okay, I think you're clear. All right, now I would like to go a little deep into that. We say standby power, right? The standby power comes from your supply voltage and the leakage current. Okay, so now we have to understand what is the leakage current is. Okay, that's what this graph explains. Okay, okay. Anyhow, I don't want to tell you more a story for analogy, but let's stop with the final one. Okay, let's say you have a tap. Okay, you have a water tap in your home. Okay, now you are in your home. You need a bucket of water. Okay, you go get the bucket, hit the tap will flow. Okay, once you hit the tap to off, the tap really off. Okay, it shuts down. Okay, when you say it's on, it's completely on. When you want to shut down, it's completely shut down. Okay, so that's the ideal condition we want the tap should be. Let's say you are in a crowded bus stand in our country scenario. Then you really want to get into a public toilet, and then you need to again get a bucket of water. Now you go hit the tap, you can get the water, and you can hit the tap again to shut down the water. But the problem now with the public crowded place is that the tap is not actually completely shut down. It doesn't obey your command to completely shut down. Okay, That is exactly the problem. Okay, when we want to turn on the single transistor in your processor, it's really on. Okay, this curve explains how slowly it on, and at certain point it reaches saturation, it's completely on. But when you really want to off, it's not actually immediately go to the off state. It go to the slowly off state, and then it remains with some leakage. Okay, the drops. It's exactly like the drops that you can find in the public, crowded place. Okay, that's the problem. Okay, our idea is to completely shut down the off-state current, which means completely. We are trying to fix this public tab problem once and for all. But we have to ask the question: why these is have always some problem? That's what the very fundamental question. Okay. In microelectronics, what we refer as a sub-threshold swing. Okay, usually if I think some of our people are from Andhra University, if you study in Andhra University syllabus, they usually show this curve in linear plot. The current is in linear scale, so you cannot be able to understand much of the physics that behind it. Okay, in linear graph you cannot be able to get it. Okay, in log graph you can be able to get it. Okay, it slowly comes down to a certain value and then remains there. Why is that? If you analytically express the sub-threshold swing, you can be able to get the log of kBt by q. Okay, this kBt by q, what we refer is a non-dimensionality factor. Okay, there is no factor that affects with your device dimension. Okay, that you can be able to change or do some modification and then reduce this. Okay, there is no such a thing. It's a completely undimensional. Okay, so it's all called. In other way, you can able to say this all in fundamental units. Kb is a Boltzmann constant. T is the temperature at which your system is working. Q is the charge of electron. If you solve this equation, you can say you can get the value of 60. Okay, so the leakage, the tab leakage is, let's say, 60. It has the value of 60. If you reduce this value to any lower value, then you can be able to completely, shut down your tab, which in turn shut down your upstate current. That in turn your standby power. That in turn, making your bad guy less trouble and then make the family running. That's the entire, deep root of the problem. Okay, so our idea is to address this leakage. Okay, all right. So my entire research is to find an ideal switching device, ideal switches that can able to solve. Okay, we already knew that this is not an ideal switch, so we have to establish what is actually an ideal switch. Okay, it's an ideal switch. Okay, the ideal switch is nothing but a tab in your home. Okay, you go hit the water is on. You go and then hit the water again, hit the tab again, and then you really want to shut down your tab. With complete shutting the flow of water. Okay? So here is the symbol, pictorial representation of what is an ideal switch and what is a normal CMOS switch. Okay, you can see in the blue, so overlaid with an ideal switch. That is the conventional CMOS that we are using now in all your mobile devices. All your Snapdragon processors are based on the device which has a flaw like this. So what we are trying to achieve is the one in the red color, not red color, it's kind of magenta color. Okay, so we are trying to achieve this magenta kind of characteristics in our device. That's what everything. It has a very 4 prime qualities. One is, the on current should be as high as the conventional, that what we are using now. And then it's called the extremely low off-state current because we are completely shut down thing. And then it has a low threshold voltage. As you can see, there are 2 points in the curve which we can say threshold voltage. Your transistor needs to produce some amount of current, whereby we can say it is completely on. Otherwise, it's off. That's the threshold current. And then there is some very quite interesting thing that we want to have. That's called subthermal switching. Subthermal switching is nothing but your device should be not depend on your external environment. For example, if you are using your phone in your home, and then if you are using phone in the northern states, the temperature difference, it shouldn't be affected by any of the temperature difference. Any minor changes makes, great impact on your device. So there are 4 qualities. We are trying to achieve this kind of 4 qualities. That's in the kind of alternative research. Okay? There are a number of ways to achieve this. Okay, I really do not want to get into each member of the alternatives. Okay, what I want to trying to say is that I would like to concentrate on one alternative things which I have worked for a long time. Okay, this graph is your conventional MOSFET, and then there is something called tunnel FET. Okay, tunnel FET is nothing but it's just a FET in which the switching, the states are controlled by quantum mechanical tunneling. Okay, and then you can have a characteristics which is compared to against the MOSFET. And there is another thing called impact ionization FET. Okay, this is something called avalanche process, and then impact ionization that you have studied earlier in your any of your physics classes. Using that physics principle to achieve a FET, achieve a switching devices. That's the impact ionization FET. Another one is called NEM FET. This is called nano electromechanical FET. Okay, so from the figures and then also from the subthreshold swings that are reported, that you can see this fellow nano electromechanical FET, can able to produce a very potential candidate. That's because it can produce subthreshold swing of less than or around less than 5 millivolt or 10 millivolt in case. The record low is 2 millivolt per decade, which is produced in paper in 2009. So NEM FET is there are 3 main alternatives. So one main alternative is NEM FET. Okay, so that's the end message here. So here is that. So in order to understand how we can able to get such a low value, okay, let's say you have stuck with 60 in your conventional devices. Now you can all the way back to 10 or less than 10. So this means huge reduction in your subthreshold swing, which means in turn a huge reduction in off-state current. It leads to all the way back to our ideal switching case. So how we can able to get it? There are 3 figures here. One is called the initial condition. The another one is called the final condition. Okay, as we are already aware, we refer usually our FET devices or BJT transistors or even all the diodes are called solid state devices. Okay, which means that all are stacked together and then bounded together in the solid form. Okay, there is no mode of water, no any other forms of matter there. Okay, but this fella has little different in its working condition. Okay, because this fella has some movable element in with him. Okay, that movable element we generally referred as a mechanical part. Okay, that mechanical part actually enables to achieve such a drastic reduction in the thing. Okay, so now you have a very simple representation. You have movable element which is connected by a spring. Okay, and then you have another fixed element. Now you apply voltage between the movable element and the for example between these 2 things. Okay, and then due to the potential difference, the equation is okay. Equation difference is given here, and then once it's once you apply the potential field, the gap between the 2 fixed element and then the movable element reduces, and then at certain point the system loses its stability, and then suddenly it collapses to your fixed electrode. All right, once it collapses to your fixed electrode, then you have a current. Okay, so now here from the point where the gap is completely open to completely closed, happens very abruptly, very fast. You cannot able to measure how fast it is actually happens in the nanoscopic or mesoscopic level. Okay, So that instability in the system produces rise to reduce the submersible current, and then in a way you can able to achieve it. Okay, there are two operations. The one operation, you put the you apply the voltage between your mobile element to your fixed element, and then it collapses to your device, and then you can get the current. Okay, so now it's called, you need water, you go and hit the water, and then the water is on. Okay, that's fine, that's really fine. Okay, what you need is, you also, when you hit again, you want to completely shut down the water, right? That's what our prime aim is. Okay, so now what we have to do is, you can reverse the voltage, and then whereby with the mechanical force pull out the movable element, and then it separate from each other, and then there is no current. Okay, it looks very easy to achieve, but it actually not. That is a very complicated problem. It comes. Okay, if you look at the surface at the microscopic level, there is something called the stiction. Okay, the stiction is nothing but a static friction between the two elements. Okay, the atoms are when the very high force moving object come and collide with the fixed an atom in the fixed electrode, it makes a very static bond between each other. Okay, this fella now again not going on. Okay, this means that our entire alternative technology is really drags down, because our idea is this could be move fast as the way it moves towards the fixed electrode. So that's one of the big problem with the thing. Okay, so this is the technology, but this technology is the potential technology. There could be plenty of chance this could be really a potential technology for a CMOS alternative, but unfortunately this got some serious problem. Okay, so I think until now what I referred is a very introduction part. Okay, so my entire work is to address this problem. Okay, if I address this particular problem, which in turn I address the major problem, the deep-rooted problem. Okay, just one problem we have, right? This is just very okay. Anyhow, this is prepared for very specialized audience, but anyhow, I'll show it to you. Maybe if you are interested, we can discuss about this slide later. Okay, this is about why this fellow stuck between this fixed electrode, why he is not moving back, what is the physics behind this. That's what the thing. Okay, conventionally this is what already reported in the literature. Right? I just show you how we can able to produce better than what we seen here is the same thing, but the movable part, you can consider it is an example of what we have so far established in NEMS. Okay, it's called non-electromechanical switches. Okay, not system, it's just switches. Okay, here the movable part is an partial nano wire, and then you can have a gate. You can apply voltage to the gate, and then it pulls down, and then you can be able to get the on current as well as off current. This is what the typical current flow is. For example, it starts with the very low current, and then at the point it suddenly collapses to your gate, and then it produces the change in the current. Okay, and then you can keep as long as you want. Once you reverse the voltage, ideally this should be reaches to the original position at the same point as pulling, but it actually do not happen. It actually happens at some different voltage, and then it reaches the value. So this point, the difference between the on and the off, what we refer as a hysteresis, that's the hysteresis meaning in general for any other hysteresis in physics. But here the mechanism, the causing mechanism is different. Okay, this is what one of the best literature paper available. It's published in Nano Letters. Okay, here is the merits and demerits of the reported switch. Okay, but this is not so far the great switch. Okay, so now we say one thing. Our title is the perspectives of 2D materials, right? So far we have discussed about 3D materials. Okay, we know what is the problem. we know what is the alternative, but we also know what is the problem in the alternative structure. So now we have to understand how to overcome this problem in the alternative structure, okay, alternative technology. So in order to do that, now we are moving to 2D materials, okay. I think so far you are a little bit quite clear about it. So this is graphene, okay. I think this is one of the very overused word in scientific community or scientific literature. At least for the last 10 years, it's, you know, there are like tons of papers produced, okay. So as like others, I am also have worked with graphene for about 6 years. My whole job is to construct a device based on this 2D guy. You know, he can be subordinate, you know, alternative for the problem in the 3D counterparts. You know, that's the simple story. Right? Why the graphene is particularly important in NEMS is, as I told you, the NEMS is essentially an electronic device, right? It can be replacement for your CMOS electronics, but the NEMS also needs in a very quintessential inherent qualities of mechanical nature, because it also partly mechanical, because it has a movable part, okay. And that is where the entry of graphene, okay. Graphene is an outstandingly best material for electronic properties. It is far beyond our conventional silicon. So mechanical properties, okay. It is single layer, but you know, its Young's modulus is like 1 terapascal, okay. It can withstand up to, you know, it's, let's say, more than 20% of its initial strain, initial 10 state strain, okay. And then it's just a carbon atom, you know, just the sp2 hybridization, and then, you know, it's kind of one of the very strongest bond in the universe, okay. So this all makes, you know, the combination of electronic, like good electronic properties versus exceptional mechanical properties, makes it as a very ideal candidate for NEMS switches, okay, which in turn needs this both of the qualities simultaneously. So that's why we move to graphene based electronic switches, okay. So here is the conventional thing. When we want to present, we would like to show only the demerits of the conventional system: very high pull-in voltage, and then low on current, and then low on-off ratio. Okay. Now this picture is from my previous group. Okay, they created all this nice simulation, like animation. Right there, it is our proposal, and then this proposal. Once we achieved this proposal, we can get a low pull-in voltage, almost zero leakage current, and then very abrupt switching. This entails the ideal switching characteristics. Okay, that's how we are addressing the problem. You can go. Okay, this project is divided into 4 parts. Okay, so step 1. This maybe looks a little awkward for the like a younger audience, those who are only bachelor and masters, but I hope you can able to make it. Let's say this is the very simple structure. This is this number, again a very simple structure, but little bit modification. And this is the 3rd step. That's my step I contributed, and there is a 4th step. Okay, but the project is already done, but we actually produce the 3-terminal switch on the net. It's already published in nanoscale. Yes, that's right. Okay, now you can see, because okay, now I believe there is some PhD guys are they already completed PhD, or they are doing PhD. There are people like that in this group. Maybe from now onwards, it will be more useful for you. Not just this technical part, how you can conduct research. Okay, once you propose the research, it looks everything nice in the paper, but it actually not. Okay, my professor proposed the idea just bearing the number one, the step number one, okay? But the step number one, we have achieved the device, we have produced the results, but we have encountered a very drastic problem. The problem is, you can say this is the graphene beam, and then here is the gold electrode, okay? We use the gold electrode to pull the the hanging graphene beam, okay? We have a very problem, okay? The problem is, once the graphene beam go on stuck, hit the AU electrode, it actually really, stuck with the AU electrode, gold electrode. That's because, your carbon atom and then the gold atom makes a covalent bond. Again, you cannot break it, That's why that is failed. Unfortunately, I don't have the results, but it is published in Applied Physics letter. Okay, you can able to get it if you want. There are problem number two. The step number two, in order to address the problem one, we move to step number two. Instead of using the gold, we are using chromium oxide as its a surface to avoid the covalent bond. Again, we have a problem. We didn't produce any nice results. That is because the chromium oxide is not a very uniform material. It is, at microscopically, it have a lot of asperities. You cannot able to control the surface actually. It's not a polished surface. It's like a small humps here and there, and then it causes a lot of problem. Also, it causes bonding, again the same problem. Okay, to address this, two steps, my initial idea is, how about you can have another 2D material, let's say graphene, and then as your contact material, also as a graphene as your suspended material. Because once this come together, this fella cannot make covalent bonds, because the graphene to graphene layers, it's only van der Waals. Van der Waals is one of the very weak force in the universe. Then if that is so, you can easily break it, okay? That's the whole idea, that's the whole physics behind it, okay? But there is a lot of problem in achieving this. What I want to tell you is, this is the reason, in first place, the low van der Waals between the stacked graphene layers. That's the reason, in the first place, we can able to peel off the graphene layer, single graphene layer. If it is a very strong force, we really fail at the very first step of producing the first two-dimensional material, which in turns, there is no Nobel award. Okay, but unfortunately, thanks to van der Waals, we are able to get it. Okay, so now we stick to step number 3, and then we'll discuss some of the results. I think this is the final part of this 30 minutes webinar. I think I took some more time. Let's finish in less than 5 minutes. Okay. Okay, there you can go. Okay, that's the whole objective of my, let's say, my life for the last 6 years. Okay, produce this kind of device and then demonstrate the graphenes, switching, and then you can say this is an alternative for CMOS. Okay, there you go. That's my initial design. Okay, you can have a graphene layer here, and then you can also have a graphene layer here, and then this is my new design, because I moved from the initial design to improved design. That's because of my initial design is a failure model. I really stick to 1 year, just that much, more than 1 year for improving this design. Okay, this all happened in the research. You stick to, if you stick to wrong idea, if you stick to one idea, then you'll end up in ducks. Okay, okay, this. Okay, okay. Here is the everything that you want to know about the system. Okay, there is a suspended beam, like it's like any other beam, bridge which has a 2 ends are fixed, like bridges in the road. But that's very macro structure. But here it's only 1 micrometer in length. Okay, it's very tiny. Okay, then you have a 500 nanometer width of your fixed electrode that can able to pull your suspended graphene. Okay. In order to first, getting into the real fabrication, we have done FEM simulation. Here is the first initial studies. I'm just showing if you are interested. Here is the first study. You can able to see there is a graphene beam, and then there's a gold electrode. Okay, if the length is too high, there are a lot of things comes when you really do research, right? First I stick to 3 micrometer length, but actually that fails because it's actually go and stick with the bottom ground when I try to suspended it. And then if I increase the width, it has another problem of peeling and then broken down and then completely washed away. Okay? There are all other failures that you can get in your PhD as well as academic researcher. Once you understand all your failures, then you can able to try to increase your productivity. Here is another image which shows how clearly it is reaches the ground when you release it. It's a graphene. Then another problem, it can also sometimes go upwards, and then it also another problem. Now, as you can see from this picture, this is very nice picture because it's actually going downwards, but it actually not hit the ground as well as it doesn't buckle up. Okay, so this we all did just to get the right dimension of your device. Okay, so it's a very time consuming process. Okay, so that's the suitable dimension. It comes after 2.5 years. Okay, once you get the dimension, you do some simulation to get what will be your voltage. What is your voltage, whether you can able to really produce a nice alternative device or not. Okay, the simulation results, and then we can say how you can get it. Okay? I did all the simulation, and then we find the suitable dimension. From the suitable dimension, roughly the parameters of your pulling. Okay, if there is anyone interested in FEM simulation for graphene, that is again another hard problem. Okay, there is nobody did FEM simulation for 2-dimensional material because all your finite element method simulations are really intended for your 3D materials. There is no actual 2D things. Okay, there will be a lot of problem either you do in COMSOL or IntelliShoot or MEMS Plus, Coventry, wherever you go, if you want to do 2D materials, especially graphene and other materials, there is a lot of problem even choosing the right property value to analyze the results. Okay, anyhow, now we are little improved. Again, get back to the slides. So we optimize the device dimension. We know what is the full-in voltage that we can able to achieve. Okay? That's the thing here. Okay. Once we are done, then we can move up with the. Okay. So in your electronic device subject, you have studied things, but you never actually get into fabrication because in India there is no fabrication facilities available. It's very limited. Here is the schematic of how we gradually progress through achieving the device. We started with the big 10 by 10 millimeter sample, and then we are using the 600 by 600 micrometer as our only writing space. In that writing space, we are able to make a 1 meter or 1.5 meter length of devices. Okay, here is the schematic image. Right, that's how it looks like. Okay, this is a little bit clear image. Okay, there is one suspended part, and there is a top part. Then the top has this structure is much efficient than the previous structure. Also, this can be potentially used for alternative for CMOS. Okay, there is the optical image. There is this device structure, and then here is the tilted view of the SEM image. Okay, as you can see, there are 2 gold pads on top of which there is a gold graphene chromium. This fixed electrode, and then this fellow here is our graphene. By using this top electrode, we are pulling this beam by applying the voltage. That's the very simple thing. Okay, if everything goes, this works well, right? There are 3 parts of the part of this curve. Okay, there is one device which has a voltage of 5.5. Okay, now as you can see, this is the initial condition. Once you apply voltage between this guy to the graphene electrode, at certain point there is no current. That's this off-state current, and then at certain point it's immediately pulled into the top electrode, and then it produces this current. Okay, once you reduce the voltage, and then it again pulls back. Okay, Now, as you can clearly see from the figure, there is some stiction exists. That's true, but as you can see from this thing, it's very steep. Okay, this means that it can reach us very quickly to the offset current. Okay, the current value here is limited. That's the manually we limit to avoid anyhow it's a lab device to avoid any further damage by causing high current. So we limit it to 200 nanoamps. Later we moved to up to 10 microamps, but we usually stick to 5 microamps as our on-state current. Okay, that's one of the another nice device. As you can see, the dimensions of the device are given here. Once you apply the voltage, it goes on then things. But this device works only 34 times. Okay? There is one thing that we didn't discuss in further. That is called this is switch, right? If you have a switch or if you have a tab, you expect it should work at least a million times, right? If it fails in 10 times, you never really called it a switch. Okay. In the NEM switch, due to the stiction, that's one of the big problem, right? If you go and then sticks, you do not have the endurance, so your entire idea is failed. So this works up to 34 times. It's one of the best devices at the time. Okay, so from the device we explain 4 of the very important things that you can understand. One is physics behind the devices. Another one is pull-in voltage variation, and then if you reduce the gap, whether you can able to achieve sub 1 volt switching or not. Okay, these are some of the most interesting aspect of the switch that we have studied. We have studied all. Also, we have produced a device which works up to not less than 50 million switching cycles. It's available in preprint archive. We are currently in submitting the paper. That's one thing. So I believe this all for a very specific audience. So I would like to stop at this point here, and then I would like to say we start with the graphene as an alternative material. Graphene is an alternative material for existing material itself. Okay, we took that, and then we find an many alternative technology. Graphene can be fit in ionization, can be fit in NEM FET. Then we try to find a suitable root problem in the NEM FET, and then we replicate the material with the 2D material, and then we can produce some nice results. Maybe the 50 million watt switching cycles are not so nowhere less achievement. It's a really good achievement. You can find the paper in preprint server. But so far, this is what I want to discuss. There is another perspective. Okay, there are a lot of things I cannot able to tell in a very short period of time. There are n number of aspects in 2D materials. Now we are moving something called twistronics. Okay, I have mentioned my initial device is failure. So from the failure device, you can able to study something useful. Okay, but anyhow, I do not have much time now. So with this, I would like to thank you all. I hope it seems now whether we can able to really produce an alternative for the CMOS problem. Okay, CMOS is like a multi-billion-dollar industry. We cannot produce in the solution in the lab scale. Okay, you are really working with one single device in the lab. Okay, it's really a very tough, very long and complicated process. There are a lot of intricacies and difficulties, converting any technology things. Okay, the place that I have done my PhD and PDF, they have a very strong industrial collaboration, and then they'll discuss their industrial counterparts, try to use these things. Okay, I'm not sure whether graphene switches will come in to replace CMOS technology, but I'm quite sure that you can the graphene based sensor can be anytime soon. Okay, there are big companies spending, even my lab spending much time to developing graphene based sensors. Okay, you can check it in online. I think I would like to thank you. Thanks a lot. I hope it's useful.
Thank you, sir. The session was wholly interesting. And we have one question for you from
Yes.
Kaushik Gautam.
Okay.
He is a BTech student. It's good to know. And he is asking the question, why is gold coated with chromium in
Okay.
to improve in
Okay.
slide number 20?
Yes, yes. Okay. Actually, we are not. This is something called you are not doing intentionally. Okay. For example, okay, I think I would like to show you a slide. I think it's very better. You can be able to understand it. Um, okay. Anyhow, very nice question. I really enjoy it. Okay. Okay. You can consider any of this slide. Okay. And now, as you can see here, this is what you start with a sample. It's called silicon, and then there is a layer of SiO2. Okay, that's how you can produce charge inversion. Okay, then you always start. It's like you buying an empty land. That land is silicon with silicon oxide. Okay, you are making construction on your land, right? That's how you are building all these things. Okay. For example, if you want to pile a very big pillar on your land, okay, you cannot go and directly put it, okay. You need something called binding material between your land to your pillar, right? The chromium is actually that kind of pillar, okay. If you want to stick gold on top of your sample, which is SiO2, you need a binding material. Chromium is the best binding material to gold. If you have again a question why we are using gold, because gold is the best conductor in the world. So as you are an electronic student, so gold is a very essential part for all your electronic interconnects. But if you want to use gold, you need something to bind, right? So that's how we are end up using chromium. Okay. So again, it's not our idea to use chromium oxide, right? We are only using chromium. Once you put the sample in, okay, as you can see here, this part is suspended. Okay, this part is suspended here. This means that you can remove the oxide from there. Okay, we are kind of involving a process called buffered hydrofluoric acid etching. Okay, this is one of the very important process. So once you do that, the chromium usually normally oxidized into chromium oxide form. Okay, that is kind of inevitable. If you understand the fabrication flow, then you can able to see this. That is why we end up with chromium oxide, chromium and chromium oxide, and that intense produces a problem in our switching characteristics. That's the thing. Anyhow, good question, I think. Yeah, thanks.
Yes, hope the question has been answered. Participants, if you have any questions, you can please ask it. Yeah, I think there is no more. So considering that, we would like to end the session. So I ask Varshini Sriram to conclude the session with the vote of thanks. Varshini, are you there?
Yes, and they are able to hear me.
Yeah. So there is no more questions. So let's conclude the session with the vote of thanks.
Yeah, sure. On behalf of everyone attending the meeting and our supporters, event organizer, and as a coordinator, I extend my hearty thanks to Dr. Jothiramalingam, Aditya Engineering College, Vizag, for sharing his precious time with us and exchanging valuable information to our active participants. The session as a whole was very informative and engaging, sir. I thank the participants who were cooperative and patient throughout the session. Hope this session was useful to the audience. Participants will receive feedback form on 26th August. Certificates will be provided to those participants who attend more than 5 sessions. Thank you all. Until next time, this is Varshini signing off. Thank you.
Thank you all. Thank you, sir. Thank you, audience, and thank you, Dr. Jothiramalingam, for your inspirational and informative talk. So with this, we will conclude the session today.